swimming pool. Now this says the bacteria count in a heated swimming pool is 1,500 bacteria per cubic centimeter. So think about how big a centimeter is. I'm going to show you. It's not perfect, but you see this little dice I'm holding up right there? This die? That is roughly a cubic centimeter. Right? That much. Right? Roughly. There's 1,500 bacteria in one of those in the swimming pool. That's what the problem is saying. They're not saying the whole giant swimming pool. They're saying that much of the swimming pool. So think about how many of these are in a swimming pool, right? Am I grossing you out? Are you never going to go swimming again? So there's a lot of bacteria in a swimming pool. Now, not all bacteria is bad. Some bacteria is good. But there's 1,500 bacteria per cubic centimeter Monday morning at 8 a.m. The count of bacteria per cubic centimeter doubles every day. Okay? So we're going to skip number 1. We're going to go down to number 2 to start. Let's fill in the table to figure out how much bacteria is in the swimming pool every day. You can use a calculator if you need to fill in the table. So like Monday at 8 a.m. is your 0, right? That's your Monday. So we start with how much bacteria on Monday? 1,500. So then the 1, that's your Tuesday at 8 a.m. How much bacteria is in your pool if it doubles? 3,000. What did you multiply by to get to 3,000? Times 2. All right, so then on Wednesday, how much bacteria is in your pool? 6,000. And then 12,000. So that'd be Thursday. Then on Friday, there's 24,000, and then Saturday would be 48. Unless I'm counting wrong. Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. All right, so that answers your question for part 1. How much bacteria is on Wednesday at 8 a.m.? 6,000 bacteria per cubic centimeter. So again, we all know bacteria is microscopic, but there's 6,000 bacteria in something that big. Times a lot for a big swimming pool. I know, it's gross. I didn't say this is not the fun problem. This is the gross problem. So suppose we want to know what is the bacteria count at 2 p.m. on Tuesday or Thursday. I lied. 2 p.m. on Thursday. That is 3 1/4 or 3.25 days after we started counting the bacteria. Can we estimate? Yeah. What do you think? So do somewhere in here, right? 3.25 is somewhere in there.
1,500.
You want to say 1,500?
Yeah.
That works for me. So we're going to estimate that there's going to be 1,500, not 1,500, 15,000 bacteria. So we're saying that it's somewhere between 3 days and 4 days, and not quite halfway between, right? So we're guessing 15,000 bacteria. We're going to figure this out in just a minute. How many bacteria are there actually on Thursday? So to be more precise, it'd be helpful if you had a function or an equation to actually count the bacteria. So let's do this, write an equation after we discover a pattern. So first, if we started with a count of 1,500 bacteria on Monday, how did we get the bacteria on Tuesday after 1 day? What did we do? Multiplied it by 2. So we took 1,500 times 2. That gave us the 3,000 bacteria that were on Tuesday. Now then, how did we find the count after 2 days? What did we do again? Multiplied it by 2. So I'm going to write it this way. We took 1,500 times 2, and we multiplied that by 2, right? That was 2 days. Okay. So that was for day 2. For day 3, you took this day 2, right? You took the 1,500 times 2 times 2 and multiplied it by 2. Do you understand what I'm writing here? I'm just not writing the numbers 3,000 and 6,000, but I kept multiplying by 2. What is the pattern? It doubles. So the pattern is that you keep multiplying by 2. Okay? So what stays the same every time I did this multiplication? The 1,500 stayed the same, right? You still started with 1,500, So what stays the same is the 1500 part. What's changing is the number of times you multiply by 2, correct? So we need to come up with an equation that says I start with 1500 bacteria and I have to multiply it by 2, an unknown number of times. Does anyone remember how we can write a formula that kind of looks like that? If not, let's see. So I'm going to take what we had here. So each one of these started with 1500, right? So that's how I'm going to start my equation. In the next part, I'm going to say P of T is 1500. Right? That was at least the part that stayed the same. And then in each one of these formulas, after the 1500, we multiplied it by 2. Just more times, right? Yeah, so I'm going to write times 2 in parentheses to the power of, we're going to use T for time. To the power of T, because that exponent means however many days I want, right? 1 time, 2 times, 3 times. Now let's check real quick. Take out your calculator, and what number from your table do you want to check? Let's check like 3 or 4. 4. All right, I want you to take your calculator and find P of 4. So that'd be 1500 times 2 to the 4th power. I want you to type that into your calculator. What do you get? You get 24,000? Yes. Yes, so you know our equation is right because I got the values from the table. Well, now that I have an equation, we can actually figure out how many bacteria are there after 3.25 days. So let's evaluate the population of bacteria after 3.25 days. So again, you're taking your 1500 times 2 to the 3.25 power. And what number do you actually get? Okay, so 14,270, and then I had 0.48. I'll do 2 decimals. Should I do a whole number or decimal? We're talking about bacteria here. A whole number. So that would be about 14,270 bacteria. All right, was that close to what we estimated? So I said 15,000. Is that pretty close to 15,000? Yeah. Yeah. So we did a good job. Do you remember seeing those equations? Kind of. It's been a couple years, but it's in there somewhere. All right. Let's grab our graphing calculators again. We're going to make a picture. Now, we're going to review a couple things on our graphing calculator here. As in how to change the window settings, how to change the scale. So we have this function, y equals 1500 times 2 to the x. I'm just going to write it that way. I know we use p and t. But we have this picture. Now, before we move on, is that going to be exponential growth or exponential decay? Growth. How do you know it's going to be growth? Just in general. Because the numbers in the table, the bacteria is doubling and getting bigger, right? So we know the general shape of our graph because we just had a quiz on that today. So we need to set our window so when I graph this function, I can see the shape of it in there. So how far, I'll give you a hint here. We're going to start at our x minimum at 0 because I really only want to see the first quadrant. How far out on the x's do you want to go? Right, the x's are our days, like time. Right, so we only went up to like 5 here. Maybe to 10? I don't think we need a ton. Maybe we'll try 10. So we'll go x max at 10. And the scale, what do you think a good scale for 0 to 10 is? 1. 1 or 2. Either way is fine. 2. You can do 2. Now, my y minimum. Again, I really only want this first quadrant in here. So maybe we do 0. Again, start positive. Now, I think where's our starting value? When we look back at the table, where did we start with the bacteria? 1500. So we definitely need to go higher than 1500. And some context clues here. If I go maybe a part farther and keep looking, it says something about 3 million. So maybe we need to at least get higher than 3 million. Right? So 4 million, yeah, we can make our y scale go up to 4 million. It's okay. million. We can go a little lower than that. No, we don't. Hold on.
1 million.
Yeah, let's go up to 4 million. It's okay. 4 million. It's not that many zeros. 6. So what do you want your scale to be? Maybe like 100,000, 500,000? What do you want to do? 100,000, 500,000? 100,000. Okay. So, just be really careful. Now let's start. We'll go through this together if you've never changed the window before in your calculator. So, when you go onto your calculator, let's turn it on. Go by typing your equation into the y equals. So we started with 1,500. Parentheses 2. Make sure the 2 is in parentheses. And your exponent has a caret. Make sure x is in your exponent. So you should at least have that in your y equals. Now, in order to change the window settings, where do you think you have to go? Window. So I hit window. You should see X min, X max, X scale, the same things that are on our paper. So make sure you carefully write the same stuff into your calculator. So we said our X minimum was 0. You can just hit 0 there and I'll retype it. The X max is 10. X scale was 1. What do we make our Y minimum? 0. Now here's where you have to be careful. X maximum, 4 million. 1, 2, 3, 4, 5, 6. And Y scale we made 100,000. 100,000. Graph. And then hit graph. Why is it what? Anyone having trouble with graphing? I don't have a similar that looks like mine has. I don't know how. It's okay. If we needed to, and we don't have to right here, but why don't we, if we wanted to, we could make our window a little bit, let's make our x's to 15. Now that we see it, let's make the x's go out to 15 for the max. I think that'll help. There, that looks a little nicer, right? So I changed the x maximum to 15. So just go back to your window, retype the x max to 15. I think it helps see the shape a little bit better. Yes. Anyone else having issues? All right. So now that I have my graph here, let's sketch it on our paper. So it's hard to see, but let's imagine this is what our graph kind of looks like, right? Okay. Now, you can use your table, you can use your knowledge. Where was the, let's label the y-intercept. So if you have to go back to your calculator here, let's go to the table really quick. At what x value does your y-intercept always happen? Not 1. 0. So if I look at x equals 0, what's the y-intercept? 1,500. What did you notice about that in the equation you wrote? That's the number right here. So let's label our y-intercept on our graph. 0, 1,500. Right, at least mark that part on your graph. Okay? So you have the shape of the graph. It's going up. Our y-intercept is at 0, 1,500. Day 0, get 1,500 bacteria. Now it says we're going to trace using our calculator. I'm going to teach you something else. So it even tells us what steps to follow. So we're in number 8 right now. And it says 1484 users. On our calculator, we're going to go. So we're back at our graph. I want you to hit the second key. So everyone hit the blue second key. Say this. And then I have to walk back and forth here. Hit second. Then it says hit calc, which is the trace button. So you all see calc above trace. Trace. We're actually going to find the value. We're going to make sure that what we calculated in our equation was right. So we're going to hit value, which is number 1. So hit enter. And for x, what does it tell you to type in? 3.25. So we're finding the value for x is 3.25. So on your calculator, you can type in where it's flashing the x, 3.25. Now when you hit enter, first you should see a little flashing cursor on the bottom. But what y value did it give you here? 14,270. Is that what we found for the bacteria count using the equation? Yeah, so your calculator can do the same thing for you. So it gave us the same answer. It said there were 14,270 bacteria. That's just showing you, one, that your equation was right, and two, there's a new feature on your calculator that might be useful for different things. So now let's keep talking about our calculator here. Now, if nothing is done, they don't put chlorine in the pool, they just keep letting the swim team come and make it more bacteria and more stinky. No offense to swim team people. If they keep going, how long until there are 3 million bacteria per cubic centimeter? Right? They don't clean the pool. We want to know when is there going to be 3 million bacteria in this little tiny bit of water. So let's write an equation in this to figure this out. So is the 3 million, would that be the number of days or what you're equal to? Okay, the number of bacteria is what you're equal to. So we would write our equation like this. 3 million equals, when does that equal to your equation, to the number of bacteria? We want to know how many days until I get to 3 million bacteria. So I'm going to tell you, we do not have the tools yet to solve that equation. We are going to learn those tools next week, but we do not have those tools yet. So for now, we're going to estimate. And it says let's use our table to estimate the number of days. So back on our calculator, we got to go to the table. Second table. Now, we need to look at the y values here to figure out when do you get to about 3 million on your y. So you need to scroll through your table here until you see around where 3 million is going to be. It is between 10 and 11. How do you know, like, what does that mean again? If it says, that's how many zeros, right? That's your scientific notation. So that's 3 followed by 6 zeros, which is 3 million. So we say somewhere between, I can't talk, 10 and 11 days is when you'll have 3 million bacteria. Do you all see that okay? Yeah. All right. So between 10 and 11 days. So that's our estimation from our table. Now, even though we can't solve that equation by hand yet, we'll learn how to. The real reason you can't do it is because we don't know how to get t out of the exponent yet. You don't know that yet. We want to know exactly when we're going to get to 3 million. So let's at least use our calculator to figure out when we're going to get to 3 million. Actually, let me go back here to my graph. It says illustrate on your graph. So here's what we're going to do. We're going to graph a second line on our calculator. We're going to graph the line. We're going to graph a horizontal line here. That is the line y equals 3 million. Why do you think that that line is going to help us solve the equation? How's it going to help us once we graph it? Because once they cross, will I be able to find the intersection point and the number of days? Yes. So let's take out our calculator. Let's go back to the y equals. And if you haven't done an intersection before, you're going to see this here. In y2, I want you to type 3 million. Just the constant line 3 million here. And then hit graph. You should get a second line across. Looks like our picture. I can use the same color. So, do you guys remember how to find the intersection point on the graph? Second trace. I'll help you in a minute, Zach. Which one of those goes where you cross? 5 intersects. So you're going to go down to number 5. Do you need help back there? Now, when you do intersection, do you guys need help? No? Okay. Now the flashing cursor, it says first curve. You don't even have to like move your cursor. Where it says first curve, just hit enter. Then you hit enter the second time. And then you hit enter a third time. You always have to hit enter 3 times. Have you done that before? 10.9. Yeah. So this is the x value. That's your time. 10.9 I'll do 10.97. I'll round it to 2. 10.97 days. Is that in between 10 and 11? Yes. So it was 10.97 days. That was the x value where they intersect. So what's the pro for using the table to estimate? You can get close. Do you think which was faster, the table or doing the intersection? Ultimately, the table was a little faster, right? So the table, it's quick. You can get close, but can you get the exact value necessarily from the table? I'd say no, right? Like we could estimate between 10 and 11, but I couldn't get 10.97. What was the pro for using the calculator? When I just did it by graphing, I got the exact value, right? So that's a good thing. You have the exact value, but a negative of that is that it took a little while. It took longer, and you may have had to like adjust your window, right? If you didn't know ahead of time, like if you didn't have me telling you, oh wait, maybe we should make our scale go to 4 million, you might not have been able to see the line, and then you would have had to go back and adjust your scale over and over again. So do you think the table and calculator are ultimately the way to go to solve one of these exponentials? I mean, it could be. For now, it is. For now, this is the best way. But we are going to learn a better way. So we're going to wrap up. We're not going to do the sound of music problem today. We'll do it tomorrow. But something to ponder, how would we do this algebraically? Right? We will get there, but not today. So let's wrap up on the bottom. This is the general form of an exponential. A times b to the x. I prefer to write the b in parentheses when we write equations, only because sometimes our b, our growth rate, is going to be a decimal or a fraction. So I prefer to write the b in parentheses. The initial value, the thing you start with, is always the a. It is the first thing you see in your exponential function. The number in front is your starting value. The growth rate, or decay rate, is your b. Okay. All right, do you remember doing these? No? Well, I guess that's okay since it gives me some